Alright guys, welcome back. Today we are talking about pressure with fluids. So last time we talked about, pressure in general. Now we're going to be talking about fluids. So when an object is submerged in a fluid, the pressure it experiences increases with depth. The pressure comes from the weight of the fluid above the object. So I think we've kind of all experienced this, especially if we've gone swimming. So if you swim and you go underwater, your ears might start to hurt or something like that because the pressure is a lot more. Also, if you just kind of like driving in really windy mountains or hills, you're going to notice pressure changes in your ears as you drive up because, again, gas is a fluid, the air is a fluid, and you're going to notice that pressure. Okay, so we're going to be talking more about this, but just a simple aside, the further you go down in a fluid, the more pressure you're going to feel. Alright, so here's a little video I made. I'm going to mute it, but I'm going to talk through it as we are watching this video. So I have this here. I have 3 holes inside as I'm making these holes with my son. And I guess you can think about which one, when I pour water into it, which one do you think is going to be jetting out of the hole the fastest? Okay, so you could kind of think about that. Where will the water come out the fastest? A, B, or C? And pause the video if you want to. I'm just going to play it here. Okay. Alright, so I asked my son. He thought A. But yeah, here we go. And yeah, we can see C is the fastest. And there's many ways, but right now the reason I want you to think about it is the pressure. Okay, there's more pressure at the one all the way at the bottom than at the top one, and that's why it goes faster. And you can actually see as the water goes down, actually the pressure becomes less and less, and this doesn't go as far. Okay, so a simple demonstration about pressure. A few other things going on here, but let's just talk about pressure for now. Okay, moving on. So the formula for pressure. Pressure is equal to the density of the fluid times gravity, that's 10 meters per second squared on Earth, and how deep it is down. So density meaning like, if we're in honey, then there's going to be more pressure on us than if we were on air or water, so on. Okay, so remember gas also is a fluid, so the atmospheric around us also has pressure. The atmospheric pressure on Earth represented by P naught or pressure naught, and that's equal to around 100,000 pascals. So if you're on sea level, you're always experiencing around 100,000 pascals kind of pressing down on us. When finding the total pressure, we need to also look at the atmosphere, so the formula will look like this. Okay, so this is kind of the general formula. Unless it specifies, like, don't think about atmospheric pressure, this is what we're going to be looking at. And if you want to look at where is this derived from, please use this link to see where it's derived from. Okay, moving on. 2 fish are swimming in their aquarium tank. The first fish has a mass of 0.25 kilograms and is 0.4 meters below the surface. The second fish has a mass of 0.18 kilograms and is 0.9 meters below the surface. Okay, so let's kind of look at this. So this guy over here is 0.4 meters below the surface. And this guy over here is 0.9 meters. This guy has a mass of 0.25. And this one over here has a mass of 0.18. Sorry, I know the color is not the best on that background. So A, what pressure does the first fish experience? So remember, pressure is equal to the amount of pressure in the atmosphere plus the density of the fluid times gravity times height. Okay, so the pressure is going to be, the atmospheric pressure is 100,000. Oops, 100,000. Plus the density, and we are in water, so that's going to be 1,000. Okay, gravity is 10. We are assuming we're on Earth. And the height for the first fish, and remember the height is the depth of how much below the surface or below the fluid. So that's going to be 0.4. Okay, so let's see what that equals. Oops. Well, okay, we'll just do it. It's going to be 104,000. 104,000 pascals. Okay. If you got that one, try to do B on your own. I'm going to do it now, so I suggest pausing the video, but anyway, I'm going to do B right now. what pressure does the second fish experience? So same formula here, but the second fish is down more. So hopefully you know that means it's going to exert more pressure. There's going to be more pressure on that fish because it's lower in the fluid. Okay, 1000, gravity 10, and this fish is 0.9. Okay, so that's going to be around 109,000 pascals. One thing that we should also know is, what should we know? That the mass doesn't matter. And that should kind of like make sense. Because, you know, when you go underwater, it doesn't mean no matter how big or small you are, it doesn't change the amount of pressure that's on you. Okay? Here's a little video about pressure. It's pretty good, so watch that if you can. It's not my video, so I'm not gonna... Okay, let's look at this example. Water is in 4 different shaped containers, ranking from least to greatest. Rank from least to greatest. Which container has the most pressure at the bottom of the container? Okay, so we're gonna be looking at this. So a few things I want to say. It's not asking for what's the amount of pressure that's on the table, okay? It's asking for what's going to have the most amount of pressure at the very bottom of the container. So around this spot right there, okay? That's what we're wondering. And you can think about it, you can pause it, but the answer is going to be they each have the same amount of pressure at the bottom of the containers. Why is that? If we look at the pressure formula, it's going to be the atmospheric pressure plus the density times gravity times the height. So they all have the same atmospheric pressure. They all have the same density. It's just water. We're all on Earth. Gravity's 10. And the depth to the bottom is the same for all of them. So that's why they're all going to have the same amount of water. A lot of people might be like, wait, but this one has so much more water. Wouldn't that exert a lot more pressure? But no. Pressure only cares about the amount of depth, okay? It doesn't matter if there's a little bit of water or a lot. Okay, moving on. Water is in 4 different shaped containers, ranking from least to greatest. Which container has the most pressure at the bottom of the container? All right, think about it. Pause it if you want to. Here we go. We're going to have from least to greatest. So C is going to be the least because the depth is going to be the least. And then it's A. And then it's D, and then it's B. Okay, and all we're looking at here and all we care about is the depth. So B is the tallest amount of fluids, so it's going to exert the most amount of pressure at the bottom of the container. I hope that makes sense. Moving on. All right, guys, let's look at this next problem. Initially, there was water in a container that exerted a pressure of 108,000 pascals at the bottom of the container. 108,000 pascals. Later, some water was added to the container, which raised the water level by 0.2 meters. Okay. 0.2. What is the pressure at the bottom of the container with the additional water? Okay, pressure. Okay, so a few things we gotta do here. I'm gonna label this 1 and 2. I'm gonna do kind of like the first part first to help us out. So we know the formula. Oops. Not that. Pressure is equal to pressure naught, which is the atmospheric pressure, plus the density of water, gravity times height. And let's figure that out for the first one. So we have pressure, which is 108,000, which is equal to the atmospheric pressure, 100,000, plus density of water, 1,000, gravity 10, height, which is unknown. We don't know what this height is. But now when we do some calculations, we can figure out that the height is actually going to be 0.8 meters. You could do it in your calculator, but hopefully that's becoming a little easier to do. Okay, so now that we do know that, we should be able to figure out what we really want, which is this right here. Same formula, the pressure at the bottom we want to figure out, P naught plus density of water, gravity, height. We don't know what the pressure is at the bottom, but we know the atmosphere is 100,000, density of water 1,000, gravity 10, and now we should know it's going to be 0.8 plus 0.2, which is just going to be 1. And this is going to be equal to 100, it's going to be equal to 110,000. Okay, So hopefully that makes sense. Moving on. All right, Pascal's principle. Pascal principle states that the pressure applied to an enclosed fluid is transmitted undiminished to every part of the fluid as well as to the walls of the containing vessel. Here's a good example of what it's talking about. I can't show it on my video because I don't own it, but feel free to check that out. And I'll kind of talk about more what this means as we do some example problems. Okay, so before we talk about this principle in hydraulics, I'm just going to say, like, okay, so when you push down on water like this, you apply a certain amount of pressure. What I want to say is, let's say we apply 1,000 pascals of pressure. That means everywhere along this water, we are now experiencing 1,000 pascals of pressure. Okay, so you apply pressure anywhere, it's going to be transmitted throughout the whole fluid. Okay, so that's a good thing to know. So whatever the pressure input is, it's going to be the same pressure output. Okay, so if we're putting 1,000 amount of pressure here, there's going to be 1,000 amount of pressure here. Yep, and now we have this formula that we're going to be using a lot, or equation. The force divided by the area initially, which is, pressure, is equal to the force output divided by the area of the output as well. And I hope that makes sense, and hopefully we saw that with the other video as well. Okay, moving on. So let's kind of use this knowledge to help us here. Looking at the following diagram on the right, let's say that A1, area 1, has an area of 0.7 meters squared, and area 2 has an area of 2.2 meters squared. If someone was to apply downward pressure onto the plug A1 of 28.5 pascals, what would the force applied to the plug of A1 equal? Okay, so for part A, we know that pressure is equal to force divided by area. We're looking for area, so maybe I'm just going to put F1 and A1. So A1 is equal to force 1 divided by P. So the force, we're looking for force, not area. Let me go backwards. So F1 is going to be equal to the pressure times the area. Okay, so the pressure is 28.5. The area is 0.7. Let me put this into my calculator. 28.5 times 0.7, and we get 19.95 newtons. Okay, so that's how much force we're pushing on this fluid, okay, which looks like water. The pressure to the plug what would the pressure to the plug of A2 equal? So again, we should know if there is 28.5 pascals of pressure right here, there's going to be 28.5 pascals of pressure all along the fluid, including this spot right here. So that's also going to be 28.5 pascals. Part C, what would the force to the plug A2 equal? So we want to know, okay, what's the force over here? So this is pretty interesting. Now I'm going to say, again, pressure is equal to F2 divided by area 2. Since we know the pressure is the same, what are we looking for? A2. So A2 is equal to force 2 divided by pressure. So the force 2, that's, we're looking for force, not area. Why do I keep doing that? Sorry about that. So we're looking for the area. So area 2. No, we're looking for the force. F2 is going to be equal to the pressure times area 2. Okay, pressure, again, like we said, is 28.5. Area 2 is given to us as 22.2. So what's the force going to be? 28.5 times 2.2. And we get 62.7 newtons. Okay, so that's something just like interesting to see, is that even though we only apply a little bit of force over here, because of this pressure law, we apply way more force over here. And some people might be thinking like, that's not possible. You can't apply 19.95 newtons of pressure and get 62.7 newtons. But what's actually happening here is it's the work principle. And what that means is, let's say we push this all the way down over here with this low amount of force. Even though we push it that much, when we push this one up with a stronger amount of force, it actually only goes up a little bit. So we're doing the same amount of work, just the only issue is the force increases while the distance decreases. And if that doesn't make sense, totally fine. Just know this is how we're going to do these kind of problems. Okay, moving on. Okay, look at the following diagram on the right. Let's say you push on the plug A1 a distance of D. How much will the plug on A2 move compared to A1? Okay, so we just kind of talked about this, the conservation of work. So we see the area 2 is much more. So since it's much more, what that means is we're going to have a greater force over here compared to this force over here. But they need to be doing this same amount of work. So if we do have a greater distance over here, this one has to have a shorter distance. Okay, so that's what it is. Smaller than distance D. Okay, moving on. A hydraulic system works to lift a car. The car and platform is located at position B. The platform and car have a combined mass of 950 kilograms. The platform at position B has an area of 50 meters squared. The platform at position A has an area of 10 meters squared. What will be the minimum force necessary to apply on platform A to lift the car? Okay, so we should know again, the pressure is going to equal the same with each other. What this means is the force that we input from A divided by the area in A is going to be equal to the force of the output over here divided by the area output. So let's put this into work. Okay, what do we know? What will be the minimum force necessary to apply on the platform A to lift it? So we're looking for that minimum force, that initial force that we put in. We know that the area is 10 meters squared. We know that the output is, so the mass of the car and everything is 950 kilograms. So we know we have to lift this. So that's going to be the mass times 10. So that's going to be 9,500 newtons. Divided by the area of this, which is 50 meters squared. And now we're just going to be doing some algebra to figure this out. I'm just going to do 9,500 divided by 50, and then I'm going to do times 10. So what I'm going to see is that force input needs to be around 1,900 newtons. And that's how you lift the very heavy things without that much force. Okay, using these hydraulic systems. Okay, moving on. Look at the diagram, look at the following diagram on the right. A2 is equal to 4A1. Okay, so the area of this is 4 times as big as area 1. If a force F was applied to platform A1, what would be the force applied to A2? Okay, so we're looking for what this force is going to be, okay, compared to this. So we should already know that the force is going to be a lot more, but the distance is going to be a lot less. It's not asking for distance, so we don't care about that. But we have that formula, force in divided by A1 is equal to force out divided by A2. So if this area over here is 4 times bigger than A1, I'm going to just put it like this. Then we could just describe it like this: 4A1. And in order for these two to be equal, that means this F out needs to be equal to 4 times whatever F in is. So it's going to be 4F. Okay, hope that makes sense. Moving on. Look at the fine diagram on the right. Area 2 is equal to 4 times of area 1, very similar. If a force 2F was applied to the platform of A2, what would be the force applied to A1? Okay, so we know this is equal to 4A1. That's what A2 is equal to. And let's do this again. F in over A1. Oh shoot. sure, whatever, we'll just do it like this, is equal to 2Fn divided by 4A1. So in order for this to equal what would be the force applied, so we can see that this is going to be half as much. So we also need this to be half as much as well. So what this force needs to be is this force needs to equal half over here. Okay, which is giving us A. Hope that makes sense. I know people have trouble with these manipulation tactics, and that's why these are honest problems, but we're doing a few of them, so hopefully you're getting the hang of it. Alright guys, let's look at this last example. So we have the hydraulic lift in question has two pistons, a small one with a radius of 0.75 meters and a large one with a radius of 2.5 meters. The small piston can handle a maximum force of 200 newtons. The question is, what is the maximum mass that the large piston can lift? Okay, so let's just see what's going on. We have the small thing here going to a large thing over here. Oops, not the best drawer. Okay, few things. The small one has a radius, I'm going to call this R1, of 0.75 meters. And we also know, I'm going to call this F1, we're going to be pushing down on it with 200 newtons of force. Okay. We're looking kind of for what is the output here. Okay, what's the maximum amount of force that this piston can lift? Well, we're not exactly looking for force, we're looking for mass, but that force is going to help us. We also know that the radius of this, I'm going to call this R2, is equal to 2.5 meters. Sorry, if that looks like a 7, 2.5 meters. Okay, so a few things we need to do here. First of all, we should know that the question F1 divided by A2 is equal to F2 divided by A2. Okay, so that's one thing we should know. The next thing though, before that, is we should know the area of a circle. Area of circle, not area of zero, area of circle. And that's going to be equal to pi r squared. So A1 is going to be equal to pi and r squared, which is 0.75 squared, which is going to give us 0.75 squared times pi, 1.77 meters squared. And A2 is going to give us pi times 2.5 squared. Pi. So that's going to be around 19.63 meters squared. Okay, and now that we found the area of these two, this should become much more easy. Okay, so we're going to be pushing down with a maximum force of 200 newtons on the smaller piston. So 200 divided by A1, which is 1.77. And this is equal to the maximum output force, which we don't know. It's going to help us find the answer. But we do know that the larger piston is 19.63 meters squared. So let's kind of put this in 200 divided by 1.77. And then I'm going to do times 19.63. And then we get that the force, output force, is going to be 2,218.08 newtons. But we're looking for the maximum amount of mass that the large piston can lift. So what we're going to do is, since this is the maximum amount of force, the mass is just going to be that divided by 10. So I'm just going to divide this by 10. And the mass is going to be, 221.81 kilograms. Okay, so I hope that makes sense. I'll see you with the next one. We're going to be talking about buoyancy, so I'll see you with that. Thanks for watching, everyone.